What if the best tool we have for understanding the universe isn't a giant telescope, but a simple, really rigorous way of thinking? In this explainer, we're going to dive into a blueprint for reality that completely flips the script. It doesn't start with what the universe is, it starts with the absolute limits of what we can ever truly know. Okay, so this is the classic philosophical rabbit hole, right? Everything you see, everything you hear, everything you think, it all comes through your own senses, your own mind. So how can you prove with 100% certainty that anything at all exists outside of that? This isn't just some late-night dorm room question. It's the fundamental problem that a really powerful intellectual toolkit was designed to tackle. So let's meet that toolkit. It's called Radical Metaskepticism, or RMS. And let's be super clear, this isn't another theory telling you we're all living in a simulation or something. Think of it more like a set of rules for building and comparing theories. It starts with that one solid thing you can't doubt. All I have is my own perception. And from there, it gives us a powerful way to decide which ideas are useful and which are, well, just noise. To see how this works, let's try a little thought experiment. Imagine I show you a rock, but then I tell you it's actually two rocks, rock A and rock B. They're in the exact same spot, have the exact same mass, the same texture. They're identical in every single way you could possibly measure or even think of. The only difference is I've given them two different names. So here's the question. Are there really two rocks there? RMS would say, absolutely not. And this perfectly shows off its main tool, the equivalence principle. The idea of one rock and the idea of two identical rocks in the same spot give you the exact same results. You literally can't design an experiment to tell them apart. So for all practical purposes, they're the same idea. And the one with fewer assumptions, the single rock, is just a cleaner, more efficient explanation. This principle gets incredibly powerful when we stop talking about rocks and start talking about the entire universe. So here's the big pivot. What happens when you take this intensely skeptical, perception-first toolkit and you apply it to the biggest questions there are in physics? What kind of reality do you end up building when this equivalence principle is your main guide? Well, you get something that looks a lot like this. The Speculative Framework on Strings and Time, or SAT for short. Now, this isn't just another flavor of string theory. It's a really bold attempt to build a model of the universe from the ground up, using just geometry and topology, all while following the ruthless efficiency that RMS demands. Okay, this is where our everyday intuition kind of gets left at the door. In the SAT framework, reality is woven from these fundamental one-dimensional things called filaments. What we see as a particle, say an electron, is really just the result of how these tiny filaments are bundled together, how they're knotted and linked up. The properties we measure, like mass or charge, are just geometric features of those knots. Our entire three-dimensional world, then, is basically a projection, like a shadow being cast by this deeper, higher-dimensional filament structure. And here's where you see just how ambitious this framework is. By describing the universe in terms of pure geometry, SAT claims it can explain the cosmos without needing some of the biggest, weirdest fudge factors in modern physics. It's suggesting that the things we call dark matter and dark energy aren't mysterious substances at all. They're just consequences of this underlying filament geometry. No new particles needed, no strange energy pushing the universe apart. But remember that equivalence principle. A cool idea is totally useless if it doesn't make predictions you can actually test. For SAT to be anything more than a neat thought experiment, it has to match the reality we actually go out and measure. So how does it stack up? And this is where it gets really interesting. This slide shows SAT's predictions for the masses of a few light particles, right next to the values we've measured in experiments. Now get this, with only a single number adjusted to fit the data, the predictions are shockingly accurate. I mean, look at the pion and the muon. That's really, really close. It strongly suggests that these geometric ideas might be onto something real. At the same time, the framework is incredibly honest about its own shortcomings. It straight up tells you where the model fails right now. For instance, the simplest version of it can't correctly predict the mass of an electron. But you know what? That's not a deal breaker. It's actually a sign of a healthy scientific idea that knows its own limits and shows us where more work needs to be done. And maybe, most importantly, the framework makes real concrete predictions that could completely break it. It says that certain complex particle shapes are basically unstable and have to fall apart incredibly quickly. So if physicists at the LHC or somewhere else ever find a stable particle of that type, boom, The whole filament model is wrong. And that ability to be proven wrong, that falsifiability, is the absolute gold standard of good science. So the particle predictions are impressive, for sure, but this framework, built on these radical foundations, leads to a prediction so counterintuitive, so profound, it forces you to completely rethink the relationship between matter, energy, and information itself. Okay, let's do one last thought experiment. Picture two books. Physically, they are identical, right down to the last atom. Same paper, same ink, same weight. One book is a copy of a massively influential text, like Newton's Principia. The other one has the exact same letters, just scrambled into complete nonsense. Now, according to all of modern physics, they should have the exact same mass, and so the exact same gravitational pull. But what does ESET predict? This is the astonishing conclusion. According to the internal logic of this framework, the book containing Newton's influential ideas would be infinitesimally heavier. Let me just say that again. The information in the book would have mass.
So, how is that even possible? Well, in SAT, gravity isn't just about mass sitting here right now. It's more like the cumulative echo of particle interactions across all of time. An influential idea like Newton's isn't just ink on a page, right? It's a pattern that has echoed through history. It's been encoded in millions of brains, sparked countless conversations, guided the building of spaceships. Each one of those thoughts and actions is a real physical cascade of particle interactions, and that vast, coherent web of interactions connected to the Principia creates a stronger gravitational tug than the random disconnected static of the jumbled book. And this just leaves us with a final, absolutely staggering question. If a framework like this is a good way to look at reality, and if coherent information actually contributes to gravity, then what is the gravitational influence of our collective stories, our art, our science? What is the actual, physical weight of human history? It suggests that the most profound things we create might not just change the world in a metaphorical sense, they might literally add to its weight.